Okay, welcome to lecture 22. And so today we're moving on to unit 3, which is covering something called the Laplace transform. And so this is an extremely useful way to solve differential equations. But before we can solve differential equations using this method, we have to learn a little bit about the background. What is the Laplace transform? What are its properties? And what is it useful for? Okay. So we're going to be learning a lot of background stuff about the Laplace transform today, from its definition, the fact that it's linear, when it exists and when it does not, and then a couple of extra pieces of information called what is a piecewise continuous function and what is this thing called exponential order. So you may remember earlier in this course we studied something called differential operators, and if you recall, these were linear differential operators that we looked at, and we could use those to write the higher order linear ODEs with constant coefficients. We could write them in a really nice and neat way. So for these linear differential operators, we use this capital L to represent that. And what they basically did is they transformed one function into another one. Okay, so we usually took the linear differential operator of y, usually in the case we were looking at, and again, if it was homogeneous, this right hand side g of x would be equal to 0, but sometimes it was non-homogeneous, right? So we had the right hand side could be some function of x. Okay, so we've looked at these linear differential operators. Okay, the Laplace transform is actually an integral operator. So it's a similar idea in that we transform one function into another function, but instead of doing that through differentiation, we're doing this by integration. So the Laplace transform is an integral operator. Okay, so if we have some function which we're calling f of t here, which is defined on the interval between 0 and infinity, so the positive real axis here, including the point 0, t equals 0, then the Laplace transform of this function f of t is defined as, okay, so a little bit of notation here. So our function is f of t, the variable here is t. Okay, we write the Laplace transform of this function f of t using this stylized L here. So this L stands for take the Laplace transform of the thing inside the curly bracket. So in this case we're saying take the Laplace transform of our function f of t. Okay, and a second way we write that is we write capital F of s. Okay, capital F is because our function we were calling lowercase f here. So the notation, or the standard notation, is write a capital letter of the lowercase letter of the function you're taking. So here we've got an f, here we've got a capital F. S is a new variable which we're going to talk about shortly. Okay, so basically both of these terms basically are saying the Laplace transform of this function f of t. Okay, but the definition of a Laplace transform of some function f of t is given like so. So we're taking this integral from 0 to infinity, so it's an improper integral because we're going to infinity here, of this exponential of minus s times t. So s is this new variable, t is our original variable, so we had this function f of t. So this exponential of minus s times t multiplied by our function f of t that we want to take the Laplace transform of. Okay, so we're integrating this with respect to this variable t, so dt here. Okay, so and if this integral converges, then this is the definition of the Laplace transform. Okay, the integral must converge. So we have some special things to account for, which we'll see when we look at some examples. This new variable s, well, this is basically we're taking a function which has variable t, and we're transforming it into a function that has this new variable s. The domain of this new function f of s is all the values of the transform variable s for which the integral converges. So the key point here is that we get a new function, capital F, with a new, which is a function of a new variable s, okay, and this operation, taking the Laplace transform of this function f of t, is fine as long as this integral converges. If the integral doesn't converge, then we have problems. Okay, so just to point out here, capital F of s was because we took the Laplace transform of the function lowercase f of t. If we were taking the Laplace transform of this function lowercase g of t, then we would write a capital G of s here to represent the Laplace transform of that function. So this is just a standard notation. Okay, and so again, I pointed out here that this integral is improper because we are integrating from 0, which is fine, but we're going to infinity. So really the right way that we should be writing this Laplace transform is as the limit as n goes to infinity of the integral from 0 to n of these things, the exponential times the function. Okay, so let's look at an example, and we'll start with the simplest case here. So our function here is just a constant function. So f of t equals 1. Obviously this is defined from t equals 0 through to t equals infinity. It's just a constant. Okay, so we want to take the Laplace transform of this function f of t equals 1. So we're taking the Laplace transform of this constant 1. Okay, and so by definition, this is equal to the limit as n goes to infinity of the integral from 0 to n of e to the minus st times 1. Okay, so e to the minus st times f of t. Here f of t is 1. So really all we're doing is we're integrating this exponential with respect to t, which as we know is quite straightforward. If we integrate the exponential with respect to t here, we just get the same thing, the exponential with respect to t repeated, e to the minus st, multiplied by minus 1 over s, okay, because we have to account for this minus s in the exponential here. Okay, so nothing too challenging there, but we need to substitute in the values of t when t is equal to n, and then take the limit, and when t is equal to 0. Okay, so if we do that, well, if e to the minus s times n, the limit as n goes to infinity is 0. Okay, if s is positive anyway, then the limit is 0. And then if we substitute in 0 here, we're just going to get e to the 0. So we're just going to get minus 1 over s, or in fact we get minus 1 over s, so positive 1 over s. Okay, so this relied on the fact that s had to be greater than 0. Okay, if s was less than 0 here, we would have had a problem because this exponential would not have converged to some finite value. It would have gone off to infinity if s was negative, because then we would have got the exponential of something that's positive. Okay, so the key point is here we have to be careful what values of s ensure that our integral, or our limit here, converges to something finite. We don't want this thing going to infinity. So it turns out that the Laplace transform of the constant 1 is just 1 over this new variable s, where s has to be greater than 0. So let's look at another example here. So we have a function f of t, which is equal to e to the at, where a is just some real number. So again, this exponential function is defined for, well, in fact for all values of t, but it's definitely defined for t between 0 and infinity. So let's look at the Laplace transform of this function, Laplace transform of e to the at. Well, by definition, this is the limit as n goes to infinity of the integral from 0 to n e to the minus st times our function f of t. So our function is, in this case, is e to the at. Of course, we've got an exponential multiplied by an exponential here, so we can combine those by summing those two arguments together into a single exponential. But we also have a constant factor in both of these exponentials of t, so we can pull that out in the exponential as well. And so we can combine this into a single exponential like so. Okay, and again we're integrating with respect to the variable t here, so we can quite easily see that that integral is just going to be equal to minus e to the t multiplied by a minus s divided by s minus a. That limit as n goes to infinity, and our integration limits are n to 0. Okay, and again if we do that, if we assume that this integral converges as n goes to infinity, well that tells us something about the sign of a and s, or at least it tells us something about a and s. Again, if we substitute in t equals 0, the second limit of integration here, this exponential becomes 0 and we're going to get 1 over s minus a. So that's what we get here. So again, this only worked if this exponential went to 0 as n went to infinity. Okay, so therefore we knew that s had to be greater than a, so that we had something exponential of negative infinity as t went to infinity, or as n went to infinity. So in this case, the Laplace transform of the exponential of a, some constant a times t, the Laplace transform of that is equal to 1 over s minus a. Okay, and that was for s greater than a. Okay, so we've got two of these now, and what we're going to do is we're going to build up sort of a catalogue of Laplace transforms, and so sometimes you'll be required to actually solve the integral. So that's what we call calculating the Laplace transform from the definition of the Laplace transform, which is shown in the top line here. So sometimes you'll have to do that. Other times, if you're just told, okay, well, what is the Laplace transform of the exponential of a times t? Well, you can just look at your table and say, well, that's 1 over s minus a for s greater than a. Okay, another example here is, well, we can take the Laplace transform of trigonometric functions. So what is the Laplace transform of sine of t? Well, the Laplace transform of sine of t from definition is the limit as n goes to infinity of this integral from 0 to n e to the minus st times sine of t dt. Again, remember we're integrating with respect to t here. Okay, so we've seen some integrals like this, right, where we have an exponential times a trigonometric function, and we knew that we had to solve that integral using integration by parts. Okay, so let's write down the integration by parts formula. The integral of u prime times v dt equals uv minus the integral of v prime u dt. So in our case, let's write down our u prime, v and v prime. Let's take u prime to be sine of t, so the second term here. Let's take v to be the exponential part here, and then let's integrate sine to get u. Let's differentiate this exponential to get v prime. Okay, if I do that, I get u is equal to negative cosine, and v prime is equal to negative s times e to the minus st. So I can use my integration by parts formula to figure out what this integral is equal to. Okay, so this is the, well, technically I've dropped the limit here, but let's remember that it's always a limit as n goes to infinity of 0, the integral from 0 to n of e to the minus st times sine of t dt is equal to u times v, so negative cosine times this exponential, so negative cosine times this exponential. It's a definite integral, so we evaluate that at n and 0, minus the integral of v prime times u dt. So minus the integral of v prime, which is negative s, negative s times this exponential here, times u, which is again is negative cosine. So we end up getting a positive s e to the minus st times cosine, which is what we have here. I've pulled out the s here because it's just a constant. The integral is with respect to t. Okay, so we get another integral that we have to calculate using integration by parts. So let's do that now. So again, I'll take u prime to be cosine of t. I'll take v to be this minus s e to the minus st thing, so the exponential term here. I'll integrate cosine to get u. I'll differentiate this exponential to get the v prime. And I quite simply get that u is equal to sine of t, and v prime is s squared e to the minus st. Okay, now I can put that in my integration by parts formula. This integral is equal to, well, u times v, sine of t times v, which is this negative s times this exponential. So this term here, evaluated at n and 0. Take away the integral of v prime times u dt. So v prime down the bottom here times u, which is sine. Okay. So this integral in purple here, I've evaluated using integration by parts, and I get this term here. So expanding all that, the original integral we started with, this, the integral of sine of t times this exponential is equal to the limit as n goes to infinity of this exponential, negative this exponential times cosine, minus s times this exponential times sine, minus s squared times the original integral, in fact. The integral of 0 to n of the exponential times the sine of t. So again, notice that we've got this same term on both sides of the equation, so we can, it feels like we've made no progress, but in fact I can take this term on the right hand side over to the left hand side, okay, and combine those like terms, okay. So I get, well, on the left hand side I've got one of these integrals, on the right hand side I've got s squared of them, so I end up with 1 plus s squared times this integral is equal to the limit of these things. So then I can divide through by 1 plus s squared and get rid of that. And finally I get that the original integral we are trying to solve is the limit as n goes to infinity of this thing here, e to the minus st minus that over 1 plus s squared times s times sine of t plus cosine of t, all evaluated at n and 0. And not forgetting that we're taking the limit as n goes to infinity. So there's a lot of calculus here, a lot of first year integration here that we probably just need to revise on if you're struggling with this. So again, assuming s is positive here as n goes to infinity, when we substitute that in, that is going to go to 0. Okay. These terms here as n goes to infinity are going to be something between -1 and 1. So this whole thing is going to go to 0 as assuming s is greater than 0 when we substitute in n and take the limit. The second limit here, as we substitute in t equals 0, well, the exponential of 0 goes to 1, the sine of 0 goes to 0, and the cosine of 0 goes to 1 as well. So we end up with simply 1 over 1 plus s squared. Okay, again, we have to make that assumption that s is greater than 0, otherwise this thing does not converge and we cannot take its Laplace transform. So the domain of this new function, capital F of s, which is equal to 1 over 1 plus s squared, the domain of that function is s greater than 0. Okay, so now we can add to our table that we've had before. We took the integral, the Laplace transform of a constant a is equal to a over s. The Laplace transform of the exponential of a of t, a times t, is 1 over s minus a. Again, that's for s greater than a. The Laplace transform of sine of some constant times t here, b is some constant, is equal to b over s squared plus b squared, valid for s greater than 0. You can do the same thing for cosine, so this is an interesting one. So sine of the Laplace transform of sine of some constant times t, you get the constant on the top, and s squared plus the constant squared. But the cosine, the Laplace transform of the cosine of some constant times t, you get the variable s on top over s squared plus b squared. So these two things are similar. Really the difference is the sine you get the constant on top, with the cosine you get the variable on top. And again, I'm not going to prove this one either, but you can if you like, you can try. If you take the Laplace transform of the variable t to some power n, so n is some integer, 1, 2, integer greater than 0, so 1, 2, 3, 4, blah, 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 up to infinity. The Laplace transform of t to the power of n is equal to n factorial over s to the power of n plus 1. So for example, if you had the Laplace transform of t itself, so t to the power of 1, you get 1 factorial, which is 1, over s, 1 plus 1 is 2. So you get 1 over s squared. The Laplace transform of t is 1 over s squared. Again, valid for s greater than 0. So we can actually take the Laplace transform of all these different functions, and we're going to look at some more as the class goes on, and in the next class as well. But the really nice thing about the Laplace transform is it's not just defined for continuous functions. Okay. In fact, we can take the Laplace transform of a piecewise function here, as long as it's piecewise continuous. And we're going to come back to that point. But let's try and take the Laplace transform of this function. So this function is equal to 1 for t between 0 and 1, and it's equal to the exponential of 3t for t greater than 1. Okay, so if I graph that function, it looks like this. So this function is equal to 1 for t between 0 and 1, and then it jumps up to be this exponential function for t greater than 1. So you can see there's a jump here, a finite jump here, and so I'm claiming that we can take the Laplace transform of this function. So let's try and do that from definition. F of s, capital F of s, is equal to the Laplace transform of f of t, which is equal to, by definition, the limit as n goes to infinity of the integral from 0 to n, the exponential of minus s times t times this function f of t. But now this is a piecewise function, okay? So what I'm going to do is I'm going to split this integral up, because I can do that, if you recall, from first year calculus. I can split this integral into two parts. I can split it into a part which is where t is between 0 and 1. Remember, t is my integration variable here. I'm integrating dt. And then I can split the integral up into the second part, which is for t greater than 1, so t from 1 to n. And if I do that, it looks like so. Okay, so my integral between 0 and 1 of e to the minus st, the function f of t is equal to 1 there. So I'm multiplying e to the st by 1 in this interval 0 to 1. Okay, so this integral is very standard, easy to calculate. But we're adding to that the limit as n goes to infinity of the integral from 1, so not 0 now, from 1 to n, e to the minus st times f of t. And so for t greater than 1, my f of t is e to the 3t. Okay, so now I can evaluate these two integrals separately. So the first one here, e to the minus e to the minus st over s, evaluated from between 1 and 0, I can do that easily, right? Plus the limit as n goes to infinity of e to the t 3 minus s over 3 minus s, evaluated between n and 1 now. Okay, so again, if assuming that s is greater than 3, this exponential term will go to 0 as n goes to infinity. Okay, so if I substitute an n for t here, take n, the limit as n goes to infinity, this is going to be 0 as long as s is greater than 3. Okay, otherwise this thing's going to diverge and there's no Laplace transform. So here s has to be greater than 3. If I substitute in 1 here, well, I'm going to get e to the 1 times 3 minus s over 3 minus s. Okay, but it's negative, right, because this is the lower limit of integration, so I'm going to get negative e to the 3 minus s over 3 minus s. Okay, and this one over here, I'm going to get negative e to the minus s over s, take away e to the 0, so it was 1. So I'm going to get 1 over s, so I'm going to get positive 1 over s. So 1 over s minus e to the minus s over s, plus this term from this second integral here. Again, remembering that this is for s greater than 3, otherwise this exponential diverges and we do not have a Laplace transform. Okay, well, there's a little bit of calculus in here from first year. What I would suggest is that you just try this yourself, and if you get stuck, flick me an email and we'll talk about it. But the key point I wanted to get across here is that we can take the Laplace transform of piecewise continuous functions. Okay, and this can be really useful for engineering applications. For example, if you've got some switch that turns on and off, well, at sometime your function f of t may be 0, and then in an instant you turn it on, so the f of t becomes on, so let's just say that's 1, and then it may turn off again and on again at different points in time. So because we can split this integral up into different pieces, we can calculate the Laplace transform of piecewise continuous functions too. So, well, when we get to solving ODEs using the Laplace transform, we're going to be able to solve ODEs which have a right-hand side or a non-homogeneous term which is piecewise continuous. And we have no other method that we've learned in this class to solve piecewise continuous right-hand sides, right? So this is going to be quite a powerful result, in fact. Okay, so again, a little bit more theory about the Laplace transform. It turns out that this transform is linear. So if we have two functions, f of t and g of t, which are functions that have Laplace transforms for s greater than some number a, and if we let alpha and beta be some real numbers, the alpha and beta are in the real numbers, so these are just constants, then the Laplace transform of, okay, I've lost a thing here, let me just fix that up. Okay, sorry about that, I just fixed this up. So if we have two functions f and g who have Laplace transforms for s greater than a, alpha and beta are constants, then the Laplace transform of the linear combination of f and g, so alpha times f plus beta times g, well, it turns out this is equal to alpha times the Laplace transform of their function f of t plus beta times the Laplace transform of the function g of t. And of course, well, that means the Laplace transform is a linear operator, and the proof is quite easy because, of course, you learned in first year calculus and possibly at high school that the integral is a linear operator as well. Okay, so you can split the integral. If we had the integral of some function plus the integral of another function, if we had the integral of one function plus another function, dt, let's say, then we can split that up into the integral of one function plus the integral of the second function. Okay, so for example, if I have the function f of t equals some constant 5 plus 3e to the 6t plus 6 cosine of 2t, and I want to take the Laplace transform of that function, I can split that up into 3 different Laplace transforms. So I can take the Laplace transform of 1 multiplied by 5 plus 3 times the Laplace transform of e to the 6t plus 6 times the Laplace transform of cosine of 2t. So the Laplace transform is linear. I can take the Laplace transform of this function f of t and split it into 3 sub-Laplace transforms, each of which is easier by itself. Okay, well, let's do this now. Let's remind ourselves what is the Laplace transform of a constant 1, and what is the Laplace transform of an exponential function, and what is the Laplace transform of the cosine? Well, from our table that we had before, see here the Laplace transform of a constant equals that constant over s. The Laplace transform of a constant times t is 1 divided by s minus that constant. And the Laplace transform of cosine of b of t, where b is some constant, is s over s squared plus the constant squared. So it turns out that the Laplace transform of 1 is 5 times the Laplace transform of 1 is 5 over s, plus 3 times the Laplace transform of 6t is 3 divided by s minus 6, plus the Laplace transform of of cosine of 2t, 6 times the Laplace transform of cosine of 2t is 6 times s over s squared plus 2 squared, which is 4. Okay, and this is valid for s greater than 6 because from this exponential, from the table on the previous slide, Well, for cosine, s had to be greater than 0. For the constant, s had to be greater than 0. But for the exponential, s had to be greater than a, where the a is the constant in the exponential. So here we had e to the 6t, so s has to be greater than 6. Okay, so just to finish up this class, we're going to look at a couple of definitions here. So the first one is, well, I said that we can take the Laplace transform of a piecewise continuous function. So just to be clear about what that is, a function f of t is piecewise continuous on some interval a to b, including a and b, if the function is continuous at every point in this domain, except at a finite number of points. Okay, so we can't have a gap. It can only happen at a finite number of points. And there the functions are permitted to have a jump discontinuity, but the jump must be finite. It can't jump to infinity. Okay. So for example, if I look at these two functions, f of t equals t squared between 0 and 1, t between 0 and 1, but it's equal to 2 for t between 1 and 2. So this function here is piecewise continuous on the domain 0 to 2, because the jump at t equals 1 is finite. So at t equals 1, here t squared is 1, and t equals 1, here t is 2. So we get a finite jump between 1 and 2. So that is a finite jump, so this function is piecewise continuous. However, the function f of t equals 1 over t has an infinite jump at the origin. So because this is going to infinity as t goes to 0. So this is not going to be piecewise continuous on any interval that contains the origin, t equals 0. Okay, and so this has to be, these jumps are allowed only at a finite number of points, okay? So for example, if I take two functions here, one, the function on the left, we get some kind of increase, and then a finite jump from 1 to 2, where after such, this function is equal to a constant 2. So there is just a jump at one point here, so this can be piecewise continuous. However, here we've got a gap, right? So between 0 and 1, t equals 0 to 1, we get this exponential increase, but then we get a jump across here. So this gap here is actually an infinite number of points, okay? So this cannot be piecewise continuous. The first one is piecewise continuous. The second one is not piecewise continuous, because even though the jump is finite, so we go from f of t equals 1 to f of t equals 2 here, we have a gap here where we have an infinite number of points when that's happening. So you can't have an infinite jump, you've got to have a finite jump, and you can't have any gaps in here if you want to have a piecewise continuous function. So it turns out that if we do have a piecewise continuous function on an interval, and the function is integrable on that interval, then the Laplace transform of the function exists. Okay, so if we have a piecewise continuous function on the interval 0 to infinity, then the Laplace transform of the function does exist. That is the theory here. Okay, so it's very useful. We can take the Laplace transform of piecewise continuous functions, and we'll see that later in this unit. The second thing I wanted to define here is something called exponential order. And so a function f of t is of exponential order, which we're calling c, if there exist constants c and m greater than 0 and capital T greater than 0, such that this inequality is satisfied. So the absolute value of the function f of t has to be less than or equal to this constant m times the exponential of this constant c times t for all t greater than this other constant capital T. Okay, so what I'm really trying to say here, using this mathematical jargon, is that our function f of t does not grow faster than an exponential. Okay, you can tell that this is going to be true for well, I guess a lot of functions, right? So exponential grows pretty fast. Most functions, for example, trigonometric functions, logarithmic functions, any polynomial, they do not grow faster than an exponential. Exponential grows really fast. Other functions, though, can grow faster than an exponential. So, for example, let's look at this case of an exponential of t squared. So we have an exponential of a polynomial here, or of a quadratic. If I look at the limit as t goes to infinity of our function f of t, e to the t squared, over e to the c times t, where c is some constant, well, I can simplify that, right, because I have, well, I know that I can, using exponential laws, I can take this exponential up to the numerator. I can pull out the common factor of t in both of these equations. I can write that as the limit as t goes to infinity of e to the t times t minus c. Okay, and this is going to be equal to infinity for any value of c, right? Doesn't matter if c is positive or negative. This is going to be going to infinity. Okay, so therefore, this function e to the t squared is growing faster than an exponential because, well, because this numerator is growing faster than the denominator because it's going to infinity. So e to the t squared is not of exponential order. It grows faster than an exponential. It's going to turn out then that we can't take the Laplace transform of e to the t squared because it grows faster than an exponential. It's not of exponential order. But let's look at a different example first, that one that is growing slower, or at least as fast as an exponential. So e to the kt, where k is a constant, times cosine of 6t. This is of exponential order c equals k. So k is this term in the exponential. Okay, so f of t is less than or equal to e to the kt here, where m is 1, because cosine is never bigger than 1. Oh, this should be capital M, sorry, but okay. Hopefully you get my point. T is greater than 0. Okay. So because this function doesn't grow any faster than an exponential, in fact it grows at the same rate as an exponential, but it doesn't grow faster than an exponential, this function is in fact of exponential order c equals k. Okay. So it turns out that if a function is piecewise continuous on the domain 0 to infinity and of exponential order c, then the Laplace transform of this function exists for s greater than c. Okay. So if you give me any function, throw a function at me, and you say, does it have a Laplace transform? I've got to check that it's piecewise continuous first, and it's of exponential order. Okay. So those are the things that need to be satisfied for a function to have a Laplace transform. It also turns out that the Laplace transform here of some function f of t, here, the Laplace transform of that function, we write as f of s. It turns out that the limit as s goes to infinity of f of s has to be equal to 0 for any function that has a Laplace transform. Okay. Any function that has a Laplace transform, the limit as s goes to infinity is always equal to 0. This is going to become important in a future class. Yeah, and we'll revisit this property of Laplace transforms. So I'll see you in the next class.